Hello friends, so today we can discuss the problem B from the latest Codeforces round 688, problem named suffix operation. According to me, this problem is a little bit difficult for B problems in Codeforces, but we have to understand this also, that if the limit of question or the bar of the questions is going high, you have to increment our practice also. And if you cannot solve some questions, then don't get demotivated. Every question which you don't solve give you some new logics and new way of thinking for every new problem. For every problem which you cannot solve will eventually help you to solve more problems. So don't get disheartened by any problem. So let's dive into the question and the tutorial of this. So you are given some array A with n numbers, and then you can take out, or you can do two types of operations. You can increase all the elements of the suffix of that array by 1, or you can decrease all the elements of the suffix of the array by 1. So what I mean by suffix x, if like you have this array, then if you take a continuous subarray like this, all the elements, in which if you take some subarray, then one side of that subarray should always end at the right end, and the other end can be at another, like any other point. If you take like these, all the elements like this, or all the elements like this, then this is a perfect suffix of this whole array. I hope you get the point. Now you can increase all the elements of the suffix. You can take any suffix, increase it by 1 or decrease it by 1, and then you have to make all the elements of the suffix equal to the same number. So that's the whole problem. If this is the only problem, then it will be simple. But you have one more constraint, in which you can change any number of this whole array to any number, like whatever number you want. Okay, so like you can change any number of this whole array to whatever number you want, and then you have to find out the minimum number of operations you have to do to make all the numbers of this array equal by doing these type of operations. Okay, so now what you can do here is, I am not actually drawing out or taking out the test cases from the problem, but I'll tell you with this drawing, and I find out that drawing of this problem will make this problem like more easy to understand. So try to draw it in terms of graph like this. Sorry, my bad drawing. Okay, just think over that we have just three numbers like this, and the first number is, let's assume that we just give some value to it. It's equal to 3, this is equal to 5, and this is equal to 1. Okay, so we have an array like this, 3, 5, 1, and we have to make all the numbers equal to some given number. Okay, if you take all the numbers as a suffix, which means like this, and if you increase all the number by 1 or decrease it by 1, then it doesn't make any sense. Why? Because if you just decrease every number by 1 or increase every number by 1, then you cannot make every number equal. I hope you get the point. So it's not beneficial to take the whole array as a suffix. But let's assume that if I take only these two elements, and if I decrease these two elements such that it will become equal to 3, because that's our only option. If I take the whole array, then it's not beneficial, but if I take the two elements, I can decrease it by 2, and then it can become like this, 3, 3, and if it decreases by 2, it will become -1. Then I will take this as a subarray as a suffix, and then increase it by 4, so 3, 3, and 3. So as you can see, I've done the number of operations equal to the difference between two every numbers. So difference between these two numbers is the operation that I did, and the difference between these two numbers is the operation I did first. So what you can see here is there is some like operations or some like observation that we have to think over the difference. Now see in this diagram, if I take this whole, like if I take this only these two bars, and if I decrease both of these bars by 2, then the difference between these two bars will not change. See, if I take both of these bars, if I just take both of these bars like this and decrease the value by 2, make this equal to this, then as you can see, though I am decreasing these bars, but this bar and the difference between these two bars remain the same. I hope you get the point. And that's the logic for this problem. The difference between every two consecutive bars will remain the same. So you can find out that if you want to make all the elements same, by like if you don't just replace out any elements, because you have the power of replacing out or changing some element, if you, without that, The answer is just the difference between every two bars, because for making the second bar equal to the first bar, you have to do this difference. Then the difference between, if now because you have made these two bars equal, you have to make these two bars equal. So which is the difference between these two bars? And then if there are some other bars, you have to like think that I have to make these bars equal to this. So the difference between these two bars, the absolute difference, because you can increase and decrease both sides. So the absolute difference between every two consecutive bars will give you the number of operations you have to do to make all the bars equal, which is fine. But now you can also change some element. So now how to think over that? Now again draw this problem out. Let's assume that I have some bars like this. The first bar is very tall, second is small, and the other is also like this. I'm not giving values, but just think over, like you can take off this to any number, like this is 5, this is like 3, this is 4. Okay, now what you can think in this problem is, if you want to make all the bars equal, you have to find out the difference between these two and the difference between these two, and then you can make them equal. But because you can also change one element, what is the best case what you can do? Because you have to take this whole suffix, this two elements, and make this increase by 2 such that this bar will become equal to 5. You can change this bar, the first bar, equal to 3 only. If you change this first bar equal to 3 only, then what will happen? Like let's assume that this is decreased, like this is not there, this part is not there. But what you can see here is, because this bar is now become equal to 3, you don't have to do the difference between these two bars, and thus the total, you have calculated the total number of operations you have to do without the replacing. You can easily calculate out by finding out a difference between every two consecutive bars. Okay, fine. But now because you have done this operation, make the first bar equal to the second bar, now you can see that the number of operations which you initially did, you have to do this number of operations, because it is equal to 5 and this is equal to 3. This is not, now this is reduced. So you have total number of operations. The total number of operations will reduce down by these two operations, which is equal to the difference between the first two elements. If you take out the difference between the first two elements, if you replace out the first element and make it equal to the second element, then this is the number of operations which is decreased from the total number of operations you will do. I hope you get the point if you are with me in this problem. Same you can do with the last element also. Just don't replace out the first element. If you don't make the first element equal to the second element, you can make the last element equal to the second last element, and that will also decrease the total number of elements. So these are the boundary conditions. Okay, but now come to the middle element. For this middle element, there are few cases you have to see. Okay, so let's assume that the middle bar is like this, and now you have like few options for the middle bar. What I mean by options is, let's draw out some another case also. Like this is the first tallest bar, like this is the second bar, middle bar, and this is the third bar. Let's think over this problem first, and then we'll go to this problem also. That for the first case, what I can do, I can make the holes, this suffix part, like, because for the boundary case there are two boundary cases. Either I can make this first bar equal to the second bar. Okay, so we don't have to do any additional changes, because and the total number of changes will decrease by the difference between these two elements. Or I can make the second bar, sorry, the last bar equal to the second last bar, such that those operations will change. Like, because you can only do one operation, one change in the element of the subarray, or the element at any point. But the next elements in between, you can also change any element in between. So what will be the change if you change any element in between two elements? Because if there can be a number of elements like this: first element, second element, third element, fourth element, fifth element, and so on. For the first element I'll tell you, for last element I've told you. For the middle elements, what you can do, like if I change any middle element, what will be the difference I can encounter? What is the maximum change I can do? See, I want to make the middle element so that if I change the middle element, the number of change, because I know the total number of operations I'll do, I have to minimize the total number of operations, such that if I change this element somehow, I have to minimize the total number of operations. How I can do? If I increase this bar, let's assume that this second middle bar is higher than both of these bars. If I have two options, I can either make this bar more taller. If I make this bar more taller, the difference between these bars will eventually increase and my total number of operations will increase only. Okay. If I make this bar smaller than this bar, like this, then also if I take this more like down, then this difference will increase and this difference will also increase, which is not beneficial. But the thing here is you have to make this bar somehow in between these two bars, and that's the optimal case. This is not a very like simple way to observe, but like you can observe it like you have only three options. For the middle element, all the middle bars, you have only three options. You can either make this bar change to something. Now you have to change this bar. You can either make this bar more taller, more shorter, or you can make this in between the two like neighbor bars. That's the only three options. Making this more taller will not help you. It will only increase the total number of operations. Decrement with the second bar will also, like, total number of operations will decrease. But if it's between these two bars, then it's optimal. Now it's optimal. Why? Because see, if I make this bar let's equal to this bar, like in between these two bars, then what will happen that I am at some middle element. I will make both of these elements. If I make both of these elements, or like even I can make this equal to this first bar. If I make this equal to this bar, or I can make this equal to this bar, or I can make this equal to the middle bar, or somewhere in between it, like they are all are same. So let's assume that if I make this middle bar equal to this bar, what is the total number of operations which is decreased? See, in the initial case, there is this bar, this difference, and there is this difference. But now, if I decrease the height of this bar to this bar, this difference has gone, and also what you can see, this difference is there, the difference between these two. So this difference is gone, and this difference is also gone, but this difference is added. What you can see here is because I have this difference, I have this difference. This difference is gone, and this difference is only remaining. This difference is also gone. So what I can see here is that I can assume that this difference is gone and this difference is gone, but this difference is added. Or what you can also say that this difference is gone twice. This difference is gone and this difference is gone, and then this difference is remained. So what is the difference remained is the difference between this height and this height. This is remained because now if I make this bar equal to this bar, then this difference is remaining, but the difference between this difference is gone and this difference is gone. I hope you get the point. See, you can draw out these test cases and then it will become more clear, because I'll draw it once again if you have some doubt. If there is some small bar, there is like this bar, which one tall bar, and there is some small bar. If I make this tall bar equal to like this bar, so initially there's a difference between them is this and this, which is the difference between every two neighbor. But now if I decrease this to this, what is the total change I can see? Initially there was this difference, or sorry, I make this equal to this bar, this building. So initially there was this like this difference, but because now they are equal, I've changed this element to this element, this difference is gone. And also for this difference is again gone, but this difference is remained, which is the difference between these two elements. So you can just total number of differences, like you can reduce this difference between this height and this height and twice it. You can also do this, or what you can do, you can decrement the difference between this height and this height and increment the difference between these heights, because see, you can assume that this height is gone and this height is gone, but this height, the difference between this and this is added, because this is only remaining, else everything is gone. So you can also like decrement this by 2, or you can like decrement these and this and then increment this by the difference between these two. So that's the logic between this problem, and then you have to check out for all the possible cases. It's just done in O of n. So if you draw this test cases, I hope you get the intuition how to solve this problem. I'll take you down to the code part now. So this is the code. Take the input of n and all the elements, and then take the input of all the elements, find out the answer. Answer is initially 0, and First we have to find out the total answer. The total answer is the absolute difference between the every two consecutive elements, which is like this. Then you have two boundary conditions. You can either decrement the total answer by the first two element difference, because if you make the first element equal to the second element, then this total number of elements or total number of operations will decrease from the total numbers. From the total number, this number of operations will decrease. Or you can change the difference between the last two elements, and both of these operations will decrement the total answer, which is the total number of operations which will do. And also for the middle elements, you will do a for loop from the second element to the second last element. What you will do, you have to always minimize the total number of operations, which is total number of operation answer minus this number of operations will decrease. What number of operations will decrease? We'll find a difference between the middle element, the middle bar, and the previous bar, the next bar. Both of these absolute difference will be decreased, and the absolute difference between the neighbor is added. Or you can find out the absolute difference between the current bar and these two, and twice it. Both of them are working fine, and the answer is just minimum of both of them. I hope you get the intuition and the code and the logic of this problem. If you still have any doubts, you can mention it on the comment box, or you can ping me on my Telegram channel. I'll see you in the next one. Keep coding. Bye.